All right, several announcements. Let me get this set up from current slides so I won't forget to do that later. All right, we don't have example 3 on the PowerPoint show, so we'll be going from here. It'll come up in a minute. Let me go over these announcements first. I don't know if they're through with this or not, but they sent this email yesterday. The business office is in the process of closing out data for our financial reporting. They said you cannot add or drop courses for students. We cannot award or process grant aid, and we cannot complete registration until further notice. I don't know if they've noticed this further or not. So if you're having trouble doing any of that, that may be the reason. All right, also on here, this is the administrative calendar. Today's the 2nd. Happy October, everybody. Only thing you might need to know, if any of you are in a first mini-term course, Friday is the last day to withdraw from it, okay? And first mini-term ends the following Friday on the 11th, which is interesting. And because they just gave us a deadline for Saturday or something, so we won't pay much attention to that. And second mini-term begins on Monday the 14th of October. I think that's more than enough information there. Now, our volleyball team, by the way, the doubleheader from last, when was it? Monday, they won both matches, so that was great. Today's the 2nd. They'll be playing Wallace State Huntsville. Unfortunately, this will be up in Huntsville at Wallace State. That'll be a 6 o'clock game, so if any of you are anywhere near Huntsville, yeah, right, near 6 o'clock, stop by and cheer the team on to victory there too. And we'll announce the rest of those next time. Now, are either of you planning to graduate this term? Do you know of anyone who's graduating this term? If you don't, well, whether you do or not, I'm going to put it on here in case anyone who's listening in. There is, you have to choose one of the following upcoming mandatory graduation meetings if you intend to graduate December 2019. Tomorrow, okay? They sent this yesterday. So we had one day, Monday, Wednesday, and one day in Tuesday, Thursday class to announce it. And this will be, if you're on the Bessemer campus, the meeting will be at 1 o'clock in Ethel Hall Auditorium. That's across the parking lot here, that building over there. And if you're on Birmingham campus, the new Academic Success Center Auditorium, and that will be a 5:30 meeting. Now, here was the part that really got me. Graduation application deadline for fall term was Monday the 30th. They sent this on Tuesday the 1st. So, I hope they'll accept them if they're coming in later. So, that one. There's a scholarship summit for fall 2019 that's coming up. Even if you're not planning to graduate this term or even this year, do you have plans? Are you an upcoming graduate? Hopefully you are at some point. Do you have plans to transfer to a university? I'm guessing most of you do. Unsure of how to pay for the remainder of your education? You may or may not be. Come educate yourself on college transfer process and transfer scholarships opportunities available from some of the leading colleges in the state. And this will be 1 week from today, October 9th, Tuesday, October 9th, at the Academic Success Center on the Birmingham West Campus, but it's right across the street from the East Campus, right across Wilson Road. And that will be from 1 to 3 o'clock next Tuesday on the Birmingham campus, and on Wednesday of next week, October 10th, that will be in the faculty and staff dining room, which is just next to the cafeteria in this building. And that will be from 1 to 3 o'clock on Wednesday. The Scholarship Summit Fall 2019 participants include Alabama A&M, Alabama State, University of Alabama at Huntsville, Birmingham Southern, Jacksonville State, Tuskegee, Miles, University of Alabama at Tuscaloosa, UAB, Mercer University from over in Georgia, Samford University from here in Birmingham, University of West Alabama, University of North Alabama, Mississippi State University, and University of South Alabama. Success is where preparation and opportunity meet. This is sponsored by Career Services, Counseling Services, and the Space Center. So all those are involved with next Tuesday and Thursday. And then the NCAS, that's NASA's Community College Aerospace Scholars Program, will be accepting applications for this year through October 16th, which is just a couple of weeks away. In fact, exactly 2 weeks away from today. Okay. One other announcement. And I don't know how much of this will affect you directly, but it certainly is going to be affecting us directly. Yesterday, I don't know if you realize it enough, Blackboard crashed. They had to do an emergency something or another to it. They got it back up, so it's running again. But evidently, it was such a severe crash, and analyzing the causes of it, let me give a little bit of history. Way back when we first got this package, I think we went with the low bid, okay? I think it was the cheapest out there, okay? And we've had it for umpteen years, I don't know how many, but quite a long time. It's probably way out of date. So we're going to have to go to, no option about it, a new package starting in January. I don't know how much of the newness will be obvious to you. Maybe none of it will. Maybe it'll be seamless for you. It will not be seamless for us, especially when we're reproducing courses and stuff like this. So stand by for issues with Blackboard, as if you haven't had enough already. Okay. Probably too much there, but let me move on. Any questions? Anything we've covered so far? All right. As we said, we're in Chapter 8, Integration Techniques and Improper Integrals. 8.1 is Basic Integration Rules, and we were on Example 3. Now, I think we had done the exploration in the margin, hadn't we, on Example 3? I think so. Yeah, I believe we did. So let's do Example 3. Find this. Oh, let me get my pen set up. Come on up. There we go. All right. The integral or antiderivative of x squared over the square root of 16 minus x to the 6. Then we'll do a dx. Oh my goodness. What an exercise. Okay. Where in the world would you begin doing something like this? Give me a guess, a hint, a suggestion. Where would you begin? Make up something. U substitution, I think, would be a good idea. What would be? 16 minus x to the 6. That would be your normal approach, I think. I thought I heard the door open, maybe not. To a U substitution. However, just let's think ahead for a moment. Then the du would be something like x to the 5th. And we're nowhere close to an x to the 5th anywhere there. So good idea, but probably not going to work too well in this problem. But it might suggest to you where we might be able to go with it. Since we won't, when we say again? Do x squared instead. Okay, really close. Okay, not the numerator x squared, but let's do this one step first, okay? And then I think maybe you'll have me a different suggestion for me, okay? I'm going to rewrite this as the integral of x squared over the square root of 16 minus, what would you like to follow that 16? Something to the 6th power? What would you like to follow it? Something to the 2nd power. What could that something be? X cubed squared. How about that? Dx. Okay? Now this one might actually involve Dawson coming in. Okay. All right, good deal. Now, if your fellow swimmer's coming today?
I think he said he is.
All right, good. I was expecting him last time and he never showed. All right, we've got sort of a problematic problem here. And as so, where would you move from there? All right, and here's the other Devin. All right, good deal. We're doing example 3 at the bottom of page 517 in chapter 8, integration techniques and improper integrals. And this is 8.1, basic integration rules. And boy, this one is anything but basic in my mind, though it does follow those rules. Now, here's a hint or a suggestion. I think we'll probably wind up, well, no, I'll take that back. I was going to say we might wind up with 2 U substitutions here, but we may not be able to. But now is a place. But what will you use as your U substitution now? That was suggested before, by the way. I didn't come up with it. Ha! X cubed. Okay, let U equal X cubed. Again, my little rule is the innermost part of the most complicated part of your problem. Most complicated part is your denominator, and that's got a radical. And inside the radical, you have a 16 minus X cubed squared. And the innermost part of that is the X cubed. So that's what I think should be the U. Then what? Du is equal to 3x squared dx. There's what we want now, except not quite. We don't have a 3 here, so let's do what? Divide both sides by 3, and that wipes this out. So this thing becomes, the numerator becomes du over 3, so let's bring the 1/3 on the outside and have the integral of du over the square root of 16 minus u squared. You see that? Now, at this point, that looks like number 18. You're absolutely right. Where A is equal to 4 and U is equal to U. Okay. It looks exactly like that. Okay. So, what will be the result of that integration? I'll pull the 1/3 out front, and that is precisely that with A equal 4. So what does that turn out being? What is it? Okay, I like to do inverse sine, or you can use arc sine, either one. U over 4 plus C. All right? But our original problem did not have a U in it, did it? So what do we need to do? 1/3 inverse sine of x cubed over 4 plus C. And that, I hope, will be the answer, and sure enough it is. Okay? And that's example 3. is what they consider basic. Okay. Stand by for the complicated stuff. Okay. We can do it. All right. Now, I don't know where they get their next statement here. It says 2 of the most commonly overlooked integration rules are the log rule and the power rule. Wait a minute, we use the power rule all the time. I don't see how they can say it's overlooked. Maybe you don't notice the log rule, but after a while you do. So notice in the next 2 examples how these 2 integration rules can be disguised in case you make a big point of disguising your integration rules. So let's do example 4. Any more questions on 3? There's your example 3. No questions, I'll erase. All right, let's move to example 4. Find this. The integral of 1 over 1 plus e to the x dx. Where would you go with this? You can look if you want at the basic integration rule. You won't find anything that looks like that too much. Okay? The closest I think you can get to it is number 5. Okay? And I'm not sure that's close enough. Okay? What's wrong with it? You don't have an e to the x up top. Okay? If you did, that would make a decent thing, let u equal 1 plus e to the x, and then you have, but then your du would be e to the x dx. You don't have an e to the x dx up there, okay? But that seems about the only, well, not the only way you can go. I was going to say there is a way to manipulate that. The trouble is, the way I was going to suggest is really complicated. The way they suggest is a lot better, okay? And it's a trick. Nothing but a trick, okay? And what is their trick?
They add and subtract e to the x.
1 plus e to the x minus e to the x. That 1, they just added e to the x to it and subtracted e to the x from it, right? That's your numerator. Denominator is 1 plus e to the x. Dirty trick at that, okay? Nothing very obvious about that until you look and say, oh yeah, that may work, okay? Because what would you do next? Okay, and what do you mean by that?
1 plus e to the x over 1 plus e to the x.
Okay. Dx, and then you'll do a minus integral of e to the x over 1 plus e to the x dx. I would say they disguised it well, wouldn't you? What's that first integral give you? 1. So the integrand gives you 1. What does the integral produce then? The integral of dx. X, okay? And then the second one, minus. Now, all right, the other swimmer makes his way in. Okay. Josh, find you. Okay. And not being a fairly decent sized class today. Now, what would you do with the second integral? You could approach it directly, or you could do a U substitution. What you want to do? U substitution. What would be your U? 1 plus e to the x. Then du is equal to e to the x dx. And that's your numerator. So that is a great U substitution to do. Tiara is here. Okay. We're only missing Fred, Ryan, and Jemiah. Okay. Hopefully they'll be coming in. Okay. So with that substitution in hand, that'll be a minus the integral of du over u, which is exactly number 5, which is log u, natural log of u, but you probably should put the u in absolute value bars, okay? But we're not dealing with u's, we're dealing with x's, so what is your u? Whoops, I put parentheses instead. Big error. Do I need to go back and put absolute value bars? Why not? E to the x is always positive. You add a 1 to it, it's going to be always positive. So yeah, we don't need absolute value bars anymore. Whoa! So you have x minus log of 1 plus e to the x. Plus c. Okay. Now, if you're tempted to say, oh, wait, let's simplify this. What is the log of the sum rule?
It's like the log of the first one plus the log of the second one?
No. There is no log of the sum rule. So if you're tempted to create one, resist temptation and leave it alone, because there is none. If that was a product, yeah, that's the log, the sum of the logs. But a sum rule, there is none. So don't even try it. Okay? It was a trick question. Okay. Intentionally trick. Okay. Sorry about that. No. Okay. So it's log, or x minus log of 1 plus e to the x plus e. Good deal. Any questions on that? Any? Okay. They have a little remark here that I think probably should have been maybe back in an algebra text many years ago, but not in a calculus text. Remember that you can separate numerators but not denominators. Now, boy, I sure hope you don't think you can separate denominators. So what we did was right. I don't even like suggesting things like that. They may put the idea in your brain and you don't need it there. And then there's usually more than one way to solve an integration problem. For instance, example 4, try integrating by multiplying the numerator and denominator by e to the minus x, and you can get a similar form. I think that's a little more, complicated, but you can look into that if you wish. Unless there's questions. Any questions on this one? Got it? So let's move to example 5. All right, to erase? Okay. Find the integral of cotangent x. I can't write. That's a pretty ugly C, isn't it? Cotangent x times the log, basic stuff here, of sine x make sure I get all the grouping symbols placed properly and correctly. Okay. Now, one of these that you run into every day, what would be your first approach? I can think of at least a couple things to do. What would you do first?
Would it help to change cotangent to cosine over sine?
That would be my first inclination. That's not what they suggest, but I think that's a good first step. So let's do that. In other words, the general form is get everything in terms of sines and cosines and then see what we can do. So this will be, all right. Good deal. Thank you. Okay. You said cosine x over sine x times, put that in parentheses, the log of sine x dx. Okay. Well, you had two trig functions. You still got two trig functions, but at least these are a little more related. First cousins, okay? What do you do from here? Any ideas? Someone has to have at least a suggestion. U substitution, that usually is a pretty good one. Let U equal what? I wouldn't do that. I'd do the innermost part of the most complicated part. Sin x. Then du is equal to cosine x. One more little part. Dx. Okay. Hey, look what that did for us. We got rid of two trig functions, and now we have it down to none because we got u's in there, and u stands for 1. So what do we have now? This will be the integral of the cosine x dx is now our du. Okay? And what do we have then? Do the rest of it for me. What do we have? Remember, u is sine x, so this will be log of u over u. Oh, yes. Okay. Now what might we do? What I've been calling it, because y'all call it that way, I've been calling it that way, but actually I just call it substitute, because not always will you want it to be a u substitution, but y'all like that because most of the time it is. This time, though, it's not a u substitution, but it's and maybe this is what Patrick was thinking all along, and if you did, good for you, okay? But in fact, that would have worked quite nicely. I would do just some other substitution, but don't use u. Use something. What would you use? Pick another letter. Not X, not U. A. Okay, strange but true. Let A equal what? And I think this may have been what Patrick was thinking earlier when he said log of sine x, and I backed off and said do just sine x, the innermost part. ln of u. Now, why does that work? Then, that's an A. My A's and U's look too much alike, so don't get them confused. This is an A, that's a U. Then, DA, that's the district attorney, is equal to, help me, that's derivative of log. Log U. Oh. Derivative of log U is? Not U. One over U du. Ha! This now becomes my dA, and that is A. Right? So now we have, if I'm not mistaken, you have the integral of A dA. And what is that? Anybody? Easiest question I've asked all day. That's the basic one here. A squared over 2. And what is A? And you can do a plus C if you want to. But what is your A? So that would be ln of U squared over 2 plus C. But what is your U? Sine x. So that would be ln of sine x squared over 2 plus C. And you could write that a couple other ways. 1/2 of ln sine x squared plus C. All right. And that's what they got to. They put the 1/2 out front. Now, I'll warn you something here. Does it look like I just put too many grouping symbols in there? Did I really need that bracket there? If you're worried about using too much pencil lead, don't worry, okay? Is that necessary or not? Is that just a waste of pencil lead?
I think it is, because if you didn't have it, it looked like just the sine x is being squared.
That the sine x would be squared, and then you could write that as 2 log sine, which is not the same thing. You do need this because it's the log function that's squared, not the sine x is squared. You're absolutely right. So you do need that extra grouping symbol there just to make sure you're squaring the log. Technically, I guess we could ln squared. You could put it there of sine x, but that is just a weird notation. I think this is a little clearer. And whether you put the 1/2 out front or over 2 here, that doesn't really matter. So yes, if we had done Patrick's suggestion and let the u equal log sine x, isn't that what you said? Okay, if you had done that, then du would have been 1 over sine x, the d sine x, which would then be cosine x. So you could have done it in one step there, but that would have been, I don't know, in my mind it was more fraught with possibilities for error in my mind. Maybe it wouldn't have been. Maybe you'd have gotten it perfectly that way. This just does one more step. And it's an unusual thing that usually you think is the denominators is part of the problem, they're part of the solution here because the derivative of log u is 1 over u. So that is what the key was there. And as I said, these are disguised, okay? in a weird kind of way. That they say was a power rule disguised, because ultimately we did do a power rule, the integral of ADA. That's the assistant district attorney if you've watched any crime shows on TV. Okay, I don't usually. Now, any questions on that? Do you need it up here a little longer? No. Okay, let's move on to example 6. They skipped a bunch of examples in this set. All right, find this one. The integral of tangent squared 2x dx. Now, does anything come to mind right off the top? In the first place always to look, especially when it's relatively simple like this, is tangent squared the derivative of something? Go back to your table and see. Nope. You may have been thinking, isn't that derivative of secant? No, it's not. Secant u tangent u is the derivative of secant. It's derivative of tangent is secant squared, but there's nothing that is whose derivative is tangent squared. So what do we do with a drunken sailor? Okay. Where do we go from here? And again, if this is basic integration rules, my word, okay, what is complicated? Any ideas there? If this were a trig class, what would be one of the first things that would come to mind? If you saw a tangent squared. Say again? Okay, sine over cosine would come to mind, but these are squared. If it's just tangent, we can do that. Okay, sine over cosine works perfectly. Tangent squared, that'd be sine squared over cosine squared, and then you got problems. Okay, sorry. It would almost work, but not quite. Think back to maybe a little more advanced in trig class, to not your quotient rule or your ratio rule, but something, what was one of the next identities you had? Any Pythagorean identities. Now, what is, does that suggest a Pythagorean identity to you? Tangent squared. I believe it was. So let's see if we can do anything with that. Equal to the integral of secant squared 2x minus 1 dx. Okay? Now, I almost gave something away by what I said earlier. Secant squared is indeed a derivative of something, isn't it? That would be tangent. Now, the question is, do you want to do a u substitution with the 2x or just deal with the 2x? Brute force without a u substitution. It's up to you. What we're going to do, if you haven't gotten it already, we're going to split this up and do secant squared 2x dx minus the integral of dx. You okay with that? Now, you want to do a u substitution for the 2x, or can you deal with it without a u substitution? Doesn't matter to me. Which way do you prefer?
Just deal with it.
Second? Deal with it? Okay. What would that suggest to you then? what function has a derivative of secant squared? Tangent. So this would be a tangent of 2x, except you got a reverse chain rule type thing here. Inverse chain rule, I don't know what you do. What would you have to do with the 2 then? This is where I wondered if the U substitution might be helpful. Remember, when you're taking a derivative using the chain rule, you multiply by your constant, basically, right? When you're undoing that antiderivative, you wind up dividing by it. So this would be over 2. Okay? Now, if you don't believe me, take a derivative of this. This is 1/2 tangent 2x. Take the derivative of that. 1/2 is still 1/2. Derivative of tangent 2x is secant squared 2x times your chain rule times a 2. Well, that 2 wipes out the 1/2. So sure enough, that is the answer for that one. And what's the answer for the other one? The easy one.
Just
X. And then what else?
plus C.
Plus C. Always have to have the plus C if it's an indefinite interval. And sure enough, that's what you got. Now, they like writing it, I don't know why, 1/2 tangent 2x minus x plus C. Just like they did in the earlier one. Put the 1/2 out there rather than over 2. Doesn't matter. All right. Any questions on that then? Okay. Along with some of the basic rules, they showed you a few tricks. Okay. Things to think about and consider. This was not quite as tricky as the other one where you add and subtract the same thing, but it's tricky enough. All right, no questions? Then we'll conclude with a summary of some of these common all right. Procedures for fitting integrands to the basic integration rules. That becomes to be the issue here. How do you make this work? Okay. One, and we saw this one, expand the wasn't the same thing. Expand the numerator. If this is in the numerator, usually a good idea to expand it. If this is something squared or something like this, go on and multiply it out. 1 plus 2 e to the x plus e to the 2x. Okay? If that was in the denominator, I would not expand. I would leave it as something squared. U squared perhaps, or something like that. Okay? Separate the numerator. This is one that we did do after we expanded the numerator a little bit. This by itself would not be a good thing to try to accomplish, but if you split that, 1 over this plus x over this, that's going to be a trig substitution in the future, okay? And this will be a u substitution right now, okay? Complete the square, especially if you have a form down here that's not one of your standard forms. Complete the square of that binomial, not the square root, the binomial that's in the square root. Complete its square, and it winds up being, there's the completed square, but then you had to add an x to that, so bring that out here, and now this becomes your u, and that's that, so that's an inverse sine. So, inverse sine problem once you have u equal x minus 1. Okay? Divide improper rational functions. Okay? Okay, I got it. This is a rational expression, but it's not a proper one because the numerator It's the same degree as the denominator. Divide first, and then you have an improper here, and you can do something with that, as in a inverse tangent type deal. Okay? Add and subtract terms in the numerator. This is the one we saw that was not completely obvious. And basically the thing to look for here, this is the more complicated part. If that's going to be your U, what's your DU? Derivative of U. If that's your U, the denominator's your U, what's the derivative of it? Come on, y'all can do a derivative, right? Derivative of x squared is?
2x.
Derivative of 2x? 2 plus 2. Well, you add a 2x up here, but you don't have the plus 2, so add a 2, but then you have to subtract the 2 to be democratic about it. Now, this gives you something you can do with a U substitution, and this gives you something you can actually do with a power rule. Believe it or not, that's the power rule. This is x plus 1 minus 2 times x plus 1 to the minus 2, and you can do that. Okay? Use trigonometric identities. We saw one before. Tangent squared was secant squared minus 1. Okay, tangent squared is cosecant squared minus 1. They just picked them out of the blue, but that's what our work study here came up to clean something off the board. She only cleaned that part, and they cleaned the whole board. Well, no, I take that back. They've had a class in here since then. She probably did clean the whole board, but whoever followed her did not do a good job with erasing. Sorry about that. And sometimes I've sort of regretted when I asked you to clean it. Well, sometimes when you clean it and someone writes on it real soon, it's smeared worse. And that may have been what happened. So use trig identities if you can, and then multiply and divide by Pythagorean conjugate. Okay to call it Pythagorean conjugate. I'd say by the conjugate, okay? And then see what falls out. If it's Pythagorean, fine. Sometimes other things will fall out. And this one, if that's what you started with, there's not much you can do with that, okay? So multiply and divide by the conjugate of that, and that gives you 1 minus sine x up here, and you have 1 minus sine squared x here, and that gives you a cosine squared x down here, Pythagorean, okay? And now you can split this into two pieces. 1 over cosine squared is secant squared, and sine over cosine squared is sine over cosine squared, and you can do that by U substitution. So, those are just some of the procedures, techniques, I call them tricks, okay? If they work more than once, call them a technique, okay? And they tend to be pretty good ones to do, okay? Any question? That finishes 8.1. Homework exercises here would include number 3, which is found at calcchat.com. Any of the odds 5 through 13, all found at calcchat.com, 7's at calcview.com. Any of the odds 15 to 45, there's a whole passel and a half of those, so do as many of those as you feel necessary to make sure you have mastery of it. They're all at CalcChat, 17's at CalcView. Then they love these things called slope fields. Even though we haven't actually done anything with this, you'll do more of this when you get to differential equations. Why they're doing it here, I'm not sure, but they are. But 47, you can try that one. They draw the thing for you there. They make you draw it in 49, and both of those are found at CalcChat. Then here's some more differential equations. Why don't we wait till differential equations to do this? This will be 51, any of the odds 51 to 55. Okay? All at CalcChat. Then do any of the odds 57 to 71. They're all at CalcChat. 59 is at Calc View. Either 73 or 75, they're both at Calc Chat. 77 or 79, they're both at Calc Chat. You can think about doing 81 if you'd like. Explore doing it, whatever. It should be at Calc Chat. And then 83 or 85, they should both be at Calc Chat. 87 should be at Calc Chat. 89 should be at Calc Chat. And then you have some applications similar to some things we've done in the last chapter. So you can do any of the odds 91 through 95. They should all be at Calc Chat. Then 97 should be at Calc Chat. 99 should be at Calc Chat. And 101 and 103, one's finding a pattern, and 103 is doing some methods of integration. One of those is computer algebra system, which I don't have, so if you have one, knock yourself out. Okay, any questions on 8.1? Okay, moving on to 8.2. Don't know why I'm so hungry today. I guess I was so busy my first 2 hours this morning. I must have burned up a lot of calories or something. I don't know. I wish. Okay. We're still in chapter 8, integration techniques and improper integrals. I was going to say improper techniques and integration integrals, but that wouldn't be right, would it? Okay, 8.2, new concept. Integration by parts. Are any of you familiar with integration by parts? You shouldn't necessarily be, but if you are, let's see if it jives with what we're doing. Our objective here is to find an antiderivative using a brand new technique called integration by parts. In this section, we'll study an important integration technique called integration by parts. Clever it's named that way, okay? This technique can be applied to a wide variety of functions and is particularly useful for integrands involving products of algebraic and transcendental functions. So if you have a product in there that doesn't appear to be anything you can integrate directly, and you think, why is this here? Now, sure, you have products, like if you had a integral of cosine x log sine x, that one comes to mind. Yeah, that's just a u substitution, because the derivative of sine x is cosine x. Yeah, that's going to work out very nicely, okay? Probably. I didn't think through it, but I think it will. But if you have a product that you can't, that one is not the derivative of the other or something like that, that you can do with a substitution or something else, then integration by parts is going to be your way to go. For instance, integration by parts works well with intervals such as x log x. If that was 1 over x log x, we can handle it, but not x log x. Integration by parts will work there. X squared e to the x. Yeah, there's no way to integrate that unless you do integration by parts. E to the x sine x, same deal. No way to do something like that. There is no function that when you take the derivative of it, you get e to the x sine x. That's just too many functions in there. So these are all products, and they're products that you can deal with. Now, before we say how to deal with them, here is what it's based on. The good old product rule. So what's the derivative of uv? Anybody? This is flashback to Cal 1. Product rule. What's the derivative of u times v? Yeah, derivative of uv. V times the derivative of u, right? And that's what they had down here, which I thought you were probably reading. Okay, so yeah, Here's one way to look at it. Now, you might say, how does that help with integration? We didn't have a sum in any of those, so how is this going to be helpful? Well, here's the deal. But u and v have to be differentiable functions of x, okay? And obviously r for that to make sense, okay? But here's what we're going to do. If your integral is one of these two, if that product, one of them's a function and the other is the derivative of the function, then what we can do is say that's the same as d by dx of uv minus, this deal, whichever one of those you're not using, okay? That's where the secret's going to come. All right? So when u prime and v prime are both continuous, you can integrate both sides of the equation. Yeah. It's just a weird, seems like they're going around their elbow to get to the ear here. Why didn't you just say derivative of uv is u dv plus v du? I mean, that's another way of saying it. And they're doing the same thing here, except it's taking them a couple steps to get there, okay? Because v prime dx, v prime is dv dx times dx will be dv, just dv, okay? So that's where that comes from. And u prime is du dx times dx, and dx's go out and you have just du. So by rewriting this equation, you can obtain the next theorem. In other words, if this is your original integral, subtract this one from this side, and you have a possible solution. Okay? That's what they do, integration by parts. If u and v are functions of x and have continuous derivatives, then the integral of u dv is uv minus the integral of v du. If this is what you're looking for, then it's uv minus the integral of v du. Now, maybe that's pretty simple to look at and see. Applying it, there's a few steps. And these steps are not hard, but after a while, they get almost second nature, okay? But at first, they may be seem a little strange. So the formula expresses the original version, the original integral in terms of another integral, okay? And it all depends on how good you are at choosing u and dv, okay? I'll give you a few little hints there. It may be easier to find the second integral than the original one, if you chose smartly, okay? Because the choice of u and dv are critical in the integration by parts process, the guidelines below are provided. Let's see how they are, okay? It says, try letting the dv be the most complicated portion of the integrand first that fits a basic integration rule. It has to be something you can integrate. Then u will be the remaining factor of the integrand. Okay, that's all right. Or try letting u be the portion of the integrand whose derivative is a function simpler than u, but dv will be the remaining factor of the integrand. Note that dv always includes the dx in the original integrand. Okay. That's a lot of blah, blah, blah. Let me try to say it what I think is a little simpler. Okay? You have a product there. Okay? The one that you let be u, what you want to do is you're going to take a derivative of u. So we want that derivative to be simpler. And most of the time it is. Okay? But the other one, the dv, you're going to be integrating that. And a lot of times when you integrate something, it gets more complicated. So try to find the dv that when you integrate it, it doesn't get any worse. Okay? Then the u, if it gets simpler, you're in good shape. Okay? So there's my suggestion. And it's almost saying the same thing here, but they just put so many words here, it gets a. You break that product into a U and a DV, and make it so that the DV, when you integrate it, it doesn't get any worse. When you take the derivative of U, it gets better. If you do that, you can do pretty well. Okay? So let's see. When choosing integration by parts, when using integration by parts, note that you can first choose DV or choose U, and that doesn't really matter. After you choose, however, the choice of the other factors is determined. So whichever one you do first. It must be the remaining portion of the integrate. Yeah, you got to get it all covered. Also note that the DV must contain the differential dx in the original equation. Yeah, that's going to be the case, and hopefully you're expecting that. All right, so let's do it. Okay, here we have a product. All right, you have an x and an e to the x. Okay, you're going to need to let the dx go with one of those. The dx will go with the dv part. Remember my rule? You want to choose the u function to be something when you take a derivative, it gets simpler. And the dv part, when you integrate it, it doesn't get any more complicated, or not much more complicated. Now, which of those, when you integrate it, will not get more complicated? X or e to the x? Okay, when you integrate x, what do you get? No, when you differentiate x, you get 1. When you integrate x, you get x squared over 2. That sounds more complicated to me. Okay? So which one of them, when you integrate it, will not get any worse? E to the x. So since you choose that to be your dv, that makes you x dx, the x be the u. So here's what we do. Now this starts like it used to. Let u equal x. And dv equal whatever is left. E to the x dx. Remember, the d's always go together. Okay? Now guess what the next step is? Then du is equal to? Now you're differentiating that. And what's that? 1 what? dx. All the d's go together, remember? Okay? Now when you integrate this one, I'll just put the integration signs there, you really don't need them. When you integrate dv, you get v, right? Agreed? And you integrate x dx, e to the x dx, and what do you get? E to the x. That didn't get any worse, did it? Okay? Now, so this is all the setup for you writing your answer down. Okay? So this thing you had to begin with is going to be uv. So you multiply these two together. That's x e to the x. But write them down in terms of the x functions. Okay? Minus, now here's what I like to call it. I don't know, maybe it's doing too much. The bottom line. Whatever you have there in the bottom. Okay? This will be your v du. Okay? So that's going to be minus e to the x dx. All right? Make sense? So, this will be x e to the x. That's done for you. You don't have to do anything else for improper integrals. And what's this one? E to the x. With one other little piece. Plus c. There's your answer. The integral of x e to the x dx is x e to the x minus e to the x plus c. Got it? Make sense? Okay. Let's see how they do it. Can I erase? Now, to apply the integration by parts, you need to write the integral in the form of a UDV. Okay? You have to decide which is going to be the U and which is going to be the DV. Okay? There are several ways to do this. X equal U, e to the x dx is dv. E to the x equal U and x dx dv. 1 is equal to U and blah blah is equal to dv. Not a good choice, okay? X e to the x is your U and dx is dv. That's sort of dumb too. I'm sorry. Won't work too well either. Occasionally you might do something like that. The last two, most of the time it's going to be one of the first two. Okay? And we've already chosen which one to do, that first one. And why? Because when you differentiate this, it gets simpler. When you integrate that, it doesn't get any worse. When you differentiate this, it stays the same. When you integrate this, it gets more complicated. So yeah, this is the way to go. Okay. I don't know why. You integrate this, you differentiate this, you get 0. How is that going to help you? How in the world do you integrate that? That's what you had to begin with. So that's out of there, okay? This one, you take a derivative of this, product rule, it gets more complicated. And integrate that, that gets a little more complicated itself. So, no, these two you don't want to do, that one you don't want to do. That one's the one to go with. Okay. The guidelines for integration by parts in earlier slides suggest the first option because the derivative of U is simpler than X and the integral of dv dx, that's the most complicated part of the integrand, it fits the basic integration formula, so it doesn't get any worse. Okay. So, we've already done this. Your dv is going to be e to the x dx. Your v is then going to be you integrate both sides, and you get e to the x. Okay? Your x is, I always do them the other way. X is, u is x, du is dx. That really got simpler. Okay? And now the integration by parts produces the first thing that you had is equal to the product of the two functions here, that function and that function, minus the integral of what I call the bottom line. They have it on the top line, your VDU. Where do they have it? VDU, okay. They don't have it on the bottom at all. It's the top or bottom. They have it sideways, okay. Right-hand side, okay. So all right, now they're turning things around. No, okay. The original problem is equal to the product of the two functions, x e to the x, minus the integral of the other combination, e to the x dx. And that's just x e to the x minus e to the x plus c dot. To check that, differentiate that and see what you get. Let's do it. When you differentiate this, product rule is going to be x e to the x plus e to the x, right? Minus e to the x. E to the x go out, you have x e to the x, which is exactly what you started with in the left-hand side. Okay. Take the derivative of c here. Okay. So yeah, that did reproduce what you had to begin with. As you gain experience in using integration by parts, your skill in determining u and dv will increase. The next summary lists several common integrals with suggestions for the choice of u and dv. They jump right to the summary. That's sort of cheating because they did example 1, they skipped 2, they skipped 3, they skipped 4, they skipped 5, they skipped 6, and went straight to the summary. I don't think that was very fair. Okay, there's going to be our greatest amount of white space. Let's do our example 2 in that. Find this. Integral of x squared log x dx. Okay. Boy, they have this way of doing. They give you a simple one they show you on the slide set, and then they jump to something that's a lot more complicated. Okay? And this does require a little more panache maybe to do. What would you suggest we go with? Choose it either way. We'll see what works. Okay, first, is that a perfect derivative of anything? No. It's a product, though, of things that you might be able to deal with. Now, remember one of their rules I didn't really focus on too much? They both need to be integrable functions. Well, differentiable functions, of course. But you will need to integrate one of them. Now, this sort of breaks the rule, but you see, you can integrate the x squared. It will get more complicated. But what happens if you tried to integrate the log x? Say again? No, that's differentiating x, log x. So in this case, since you need to integrate the dv part, you can't put the log x in the dv because I don't know what to do with it then, because there's no rule that what's the integral of log x. So guess what we're going to need to do then? That's how we always start. So which you want to be what? Pretty exciting stuff, isn't it?
Let u equal log x.
Log x. Unfortunately, you have to take the thing. This dv is going to get more complicated. Sorry about that. X squared dx. The d's always go together. Okay? And what do we do next? Then du is equal to, second, 1 over x dx, and v is equal to x cubed over 3. All right. Big boo hiss there because that's more complicated. But what happens next? What does that make your integral? uv, the basic functions, that's 1/3 x cubed log x. Okay, that's complicated, but yes, that's your answer. That can be complicated, okay? Minus, and what happens here? Well, you still got a 1/3, so I'm going to pull that out. That's a third, okay? The integral of what? What do you have left then?
X cubed.
Not quite. Your bottom line here, right?
So x squared.
Yes, this one wipes one of those out, and that would be the integral of x squared dx. And you have a 3 out front, which maybe I shouldn't have taken out front anyway, because what does this give us? This part of the answer is your answer. 1/3 x cubed log x minus, I'll put the 1/3 here. Yeah, you're going to need it anyway. Does that integrate?
It's
X cubed over 3. One more thing. plus c. Okay, so that's going to be, let me pull out, I don't know, I'll leave it in there. 1/3 x cubed log x minus 1/9 x cubed plus c. Or you could have pulled out 1/3, you know, and left it 1/3. I don't know. How do they leave it? All this time they've been pulling out the fractions, now they leave it in. X cubed over 3 log x minus x cubed over 9 plus c. They're both correct answers. And the technology part over in the left margin says to graph that. Yes, one of my favorite things to graph. I'm really rushing to do so. I'm not going to mess with that. You need graphing utilities, so I don't have one. Okay, one surprising application of integration by parts involves integrams consisting of single terms. Ooh, as in log x dx or inverse sine of x, arc sine of x. Okay? That's what we're going to do next. All right, to erase. Example 3. Okay. We go to 1140, right? Okay. Example 3. Now this one is different in a couple of ways. One is a definite integral, which we haven't done in by parts. So there is a new twist to it there. I'll put it that way. So here's the integral from 0 to 1 of the inverse sine. I like to do inverse sine of x dx. All right.
We're still going to start the same way, right?
What's that?
We're still starting the same way, right?
Yeah. Now that doesn't look like it would need it, does it? Except that, do you know a function whose derivative is an inverse sine? I don't. So, therefore, I don't know what else to try but integration by parts. So which are you going to let to be what? Let u equal and dv equal inverse sine of x, or arc sine of x. And dv is just simply going to be dx. You got to get the d's, keep the d's together. Now the problem with this is you have to know what the derivative of sine x is. Inverse sine x. Does anyone know? Okay. Go back and look in a table. Okay. Inside front cover of your book, derivative of arc sine, inverse sine, that's going to be number 19 right there. There u is our x, and derivative of x with respect to x is just u's. Derivative of x with respect to x is 1. So the u prime on top is just going to be 1. So this will be 1 over the square root of 1 minus x squared dx. Okay? Yeah. What they're calling u prime, we're calling dx. Okay? So, how about the next one? dv equal x. When you integrate both sides of that, what do you get? Amazingly easy if you think about it. Integral undoes the derivative. V is equal to x. Perfect. Okay. So now we can basically write down our answer with a little bit of help from our friends. You do the u times the v, and that's going to be x times the inverse sine of x, u times v. But here's where the big but comes in. These you have to evaluate from 0 to 1. Not just the integral, this you have to evaluate from 0 to 1 as well. And then you have minus your bottom line here. And that would be the integral, again, from 0 to 1 of x over the square root of 1 minus x squared dx. Okay.
So why do we have to do
What's
0
that?
to 1 on the first one?
That's that.
Why do we have to do the 0 to 1 on that first part?
Because it's a definite integral and you have to. They didn't tell us that, but you have to do it. You do everything there. They wait until the very end after you do it and then do the entire integral from 0 to 1. And maybe that makes more sense that way, but I'm used to doing it this way because otherwise I tend to forget to. So you need to evaluate the x's. That's what that does for you. So when you plug in a 1 here, what do you get? X becomes 1, and this would be the inverse sine of 1 minus 0, right? That's a rather strange number, but it is a number. That, by the way, is actually, we can evaluate that. We will. We'll come back and do that in a moment, okay? Minus. Now we have to fiddle with this. Oh my goodness. What in the world is that? How would you do that integration? Say again?
We can rewrite it to where we don't have the square root in the denominator.
Say that one more time.
Rewrite it where we don't have the square root in the denominator.
Okay.
Like change it to x times 1 minus x squared to the negative 1/2 power.
Okay. I like the idea, so let's do that and do it this way, if it's all right. Okay, I'll try to do it exactly like you. We'll do 0 to 1, remember we got those. X times 1 minus x squared to the 1/2 power, right? Is that what you're saying? Dx. Is that what you said? Okay. So again, negative 1/2, you're right. I was thinking of putting in the denominator with 1/2, but numerator with negative 1/2. Very good. Now what would you do with that? Let's go and evaluate this. What is the, okay. Remember an inverse sine, you can say the sine of an angle is equal to a number. So the inverse sine of a number is equal to an angle. So the question is, what angle do you have when you take the sine of it, you get the number what? Pi halves, exactly. So this just becomes pi halves. Minus, okay? Well, before I do that, in fact, I think we can get by without doing it. How would you do that integral now? Any technique come to mind? U substitution sounds like a winner to me. Let U, and this is not an integration by parts, it's a straight U substitution. Let U equal 1 minus x squared. Okay. Then du is equal to negative 2x dx. Perfect. Well, we got an x dx here. All we have to do is divide by negative 2. All right. So now we have a pi halves. Don't forget your pi halves. Now, you're going to be pulling out a negative 1/2, but you already have a minus on there, so that becomes a plus 1/2. Okay, and then you have the integral. Okay, but we got a problem, Houston. We've changed to u. We also need to change our limits. So when x was equal to 0, what's u? 1. When x is equal to 1, what's u? Whoops! We're integrating from a big number to a small number. We're going to have to flip again. And we will. But what's inside now? U to the negative 1/2 du. Because the du we already took care of here. Okay, x dx. Okay. Now, since we have to change the integral again, this is going to be pi halves. Don't forget that. When we flip the limits, we're going to reintroduce the minus sign. 1/2. Okay. Now what's the antiderivative of u to the minus 1/2? U to the 1/2 times 2. You're absolutely right. Okay, divided by 1/2 is times 2. Evaluate that from 0 to 1 because we flipped them, and so we got those back in the right order. Okay, well, first off, the 2 is now going to cancel out that, so we have a pi halves. That's been hanging around a while. Minus, you plug in 1. What's the square root of 1? 1. And what's the square root of 0? 0. Okay, so there's your answer. Part of the answer to your question, why do you have to evaluate this? Because when you have a definite integral, you're supposed to get a number for an answer, right? You can't have x's in there, so you have to evaluate that, right? Okay. Let's see what they did. Did I forget even to check my answers before? No, I think we got it right. Okay. What we got here is pi halves minus 1, which they said is about 0.571 because pi halves, half of 3.14 is 1.571, blah, blah, blah. All right, so that was example 3, and I think we have run out of time, haven't we? So what we'll do next time is start with example 4. Any questions before we make assignments here? Homework exercises here in 8.2. Any of the odds 5 through 9, they're all at Calc Chat. 5's at Calc View. Either 11 or 13, they're both at Calc Chat. 11's at Calc View. Any of the odds 15 to 33, they're all at Calc Chat. 15's at Calc View. You can do 35 and 37 if you wish. They just jump right into these differential equations, and they're fairly easy to do, but I'll let you figure out. They should both be at Calc Chat. 39 should be at Calc Chat. 41, you have to draw your own slope field, which is a real big pain, and that should be at Calc Chat. And you can try any of the odds 43 to 51, they're all at Calc Chat. 45's at Calc View. Hang off there. We will pick up the rest of those next time. Okay. Any questions? All right, good deal. Let's close it.